All right, so for this question, what we've got is a pulley with a string wrapped around it, and that string is hanging down, and then that's attached to a mass. We know the mass of the object, m. We know the radius of the pulley, r. We know the acceleration of the mass, right? We're looking for the tension in the string and just the full-on rotational inertia of the pulley. So for this question, we've got actually two different objects, right? We've got our mass, which is in just translational motion. So the forces look like that. And we've got our pulley, which is in rotational motion. And there's a torque acting on it. The torque is from the string pulling down. So just like the last question, we can set up several equations. In this question, though, we're looking at two separate objects, right? One in translational motion, one in rotational motion. But the angular acceleration of the rotating object is going to be related to the translational motion of the object in linear motion. So let's start here, right? This object, we can use net force equals ma to understand its motion. The net force on that object is just going to be mg minus t. That's going to be equal to ma. And I think the first thing they asked us to solve for is tension. We know m, we know a, right? A was given, the a of this. So we can actually solve tension really easily. Right? If we rearrange that equation, we just get t equals mg mg minus ma, right? I moved t over there, and I moved ma over here, and then I flip-flopped the whole thing. That's kind of confusing. Okay. So we've got t equals mg minus ma. And now we're looking for the rotational inertia of the pulley. So for that, we can write another equation using net torque for the pulley. Now notice the pulley, right? The pulley has a tension force acting on it, pulling down right here. The pulley also has its own weight acting down at the center of mass. And there would be a force upward from the hinge holding up the pulley. And if you summed these, right, this plus this would actually have to equal that because the pulley is not translating, right? It's rotating, but it has no translational motion, so all those net forces should equal 0. But notice that these two forces acting at the hinge, that rotation point, maybe we shouldn't call it a hinge, maybe we should call it actually an axle. But either way, right, these forces are not going to exert any torque because they're at the axis of rotation. So if we come to write our equation here for net torque, well, we know the radius of the pulley is r, so we can say that the torque from the string on the pulley is r times tension force, and that is equal to I times alpha. And now we want to solve for I, so I equals r times tension over alpha. We don't know alpha, but we know a. And remember, a should be equal to r times alpha. So alpha is a over r. And if we plug that in here for I, right, I is equal to RT over a over r. Yes, I'm just checking to make sure that's right. So that's basically r squared t over a. So now we get I equals r times t. T we found in the other part of the question. It's mg minus ma. And all of that over, wait, did I forget something? Yes, I forgot my squared. R squared times t over a. And that should be my I, right there. And let's just check the units to make sure it's right. So here, right, if we think about I, right? For something, it's like mr squared or some coefficient times mr squared. So the unit should be kilograms times meters squared. And if we look in here, right, all of these terms have some acceleration value like g and a. So those will cancel out. And then we've got like a meters squared times a mass, right? So we've got mass and meters squared. So yeah, we can get that I. And actually, I think we can simplify even a bit more if we wanted to. So let's just go ahead and do that to see what it would really look like if we pretty this up a little bit. So one thing we can do is we can take out the m. So we've got mr squared. And we've also got g minus a over a. So we could write it like that, or we could write it like mr squared g over a minus 1. All right, I hope this was helpful.